Okay, everyone, welcome to our ISR colloquia. Today's speaker is our good colleague, Professor David Lovell. Just a very brief background about David's experiences and expertise. David has a BA in mathematics from Portland State University and master's and PhD degrees in civil engineering from University of California, Berkeley. He has worked in transportation consulting, and he was also a combat engineer with the U.S. Marine Corps. I actually didn't know that. His research interests include facility design, management and control, computational and differential geometry, numerical methods, and probabilistic structure of sports and tournaments. David is also a co-PI on our brand new NEXTOR project that was funded earlier this year in collaboration with Professor Michael Ball, and the two of them are now leading this very exciting activities, and I'm guessing that he would be talking about it maybe briefly as part of his presentation. So, with no further ado, David, please.
Thank you very much. Thank you all for coming. What we call the NEXTOR group here at ISR has been around a little bit over 10 years, working on a variety of aviation-related problems. When it started up about 10 years ago, it was a consortium essentially of these 4 schools here in the middle, and somewhere down the road, George Mason got added. For a long time when we talked about the name NEXTOR, what we meant was this group of 5 universities, and as Rizak alluded to, just this last year we had to recompete this arrangement, and we went with the same group of 5 that we had had before, plus we threw in 3 more. I didn't put in the 3 more because on this page because we just started, and a lot of what I'm going to talk about today is stuff that we have done. So I don't want to give anybody any credit for anything that they weren't playing along with. But our strategy was to go find sort of 3 other schools that were really, really busy in this area and make sure that they couldn't compete against us, so get them on our team instead. So we added Georgia Tech, Purdue, and who am I forgetting? Ohio State University. So that's this group across the top. The group across the bottom is essentially our partners and the people who give us money. So primarily we get a lot of our funding from the Federal Aviation Administration and NASA. They tend to do 2 different kinds of things. The FAA is mostly concerned with, well, how are things running today? What are we going to do today? What are we going to do tomorrow? And NASA is looking a little bit more into what are we going to be doing 15, 20, 25 years from now. But there is a lot of overlap between the 2. In terms of people that we have partnered with on individual projects, the list is here. There might be more than this, but these are the primary ones. Of note are IAI, Intelligent Automation Incorporated, who happens to be the sponsor of this seminar series. And I was working with them actually on vehicular traffic stuff before I or they became interested in aviation, but we sort of came back together at some point later and did some aviation projects together. Most of these others you would recognize. This is a little consulting group called GRA, and this is the Maryland Aviation Administration, so the state version of this federal thing. So what I want to talk about today is there's this thing out there that you may have heard about, and certainly you have probably read some stories that are related to it, this idea called the Next Generation Air Transportation System. It's more than just a set of words. It's an actual program that's active at the federal government level, and it has some promise of changing maybe not your direct experiences as you fly, but hopefully how much time you sit around waiting while you fly. And certainly it will have an impact on the 2 people who are sitting in the front of the plane and doing various things that are sort of transparent to you. But I want to talk about what's coming, and then in particular what we're doing that plays any part of a role in that. So here's how I had parsed what I wanted to do today. Tell you a little bit about the group that we have here in Maryland, who we are, tell you a little bit about this new idea, where we're going, and what we've been doing to get it there. We do a few different flavors of work ourselves. We work on these things called traffic flow management initiatives. I'll tell you a little bit about that. We do a lot of work in predicting and evaluating how the system as a whole is performing at individual airports and overall, and even for specific carriers and even for specific flights. And then we're also doing some work on developing new procedures. So here's a picture of a chunk of the group as it stood outside some winery in Napa Valley. So since we're at a winery, you can imagine Mike Ball's leading the charge. Here's Andy Churchill, recent PhD graduate and postdoc. Here's me with no drink, making sure that these guys don't get in any trouble. And then a few of our other recent, all of these guys, everybody else is a PhD graduate from our program. This is our list of current students. Karina is here someplace, and then the other ones are all out goofing off someplace. So this is about the size of the group that we normally have operating. We've had a footprint that's a little bit bigger than this at times. We've been up to maybe 7 or 8 students simultaneously. But the people who sort of stay through the whole thing are Mike Ball and I, who are here at ISR, and then Bob Hoffman, who's a researcher at Metron Aviation. He got his PhD under Mike a number of years ago, and they have a nice relationship with ISR, and when he can, he comes here about a day a week and does a lot of work with us, and we've had a lot of joint projects with them. This is a list of other people on the campus, other faculty on the campus who at various times over the last, 10 or so years have been involved as partners in some of our projects, including Mark, who's right here in the room, and a bunch of other people from business school, economics, and other places. And this is a slightly longer list of our recent graduates, some of whom have gone on to academia, some of whom are working for the government, some of whom are working for private companies, and some of whom are not doing much in aviation anymore, as fate sometimes dictates. So, let's talk a little bit about what's happening in aviation. I pulled 2 pictures off the internet that are sort of crystal ball attempts to give us a clue as to where we think things are going in the sort of distant future. Here's 2010, about 700 million people were flying in 2010, and the most recent forecast from the FAA says that's going to nearly double about 20 years from now. If you had asked them several years ago, they were saying triple. And then because of the economy and things like that, they've had to revise their projections. You might think, well, who says that going from 3 to 2, that sounds like a pretty big step. I don't know if I can trust those numbers at all. I have a picture in a second that might make you a little bit more comfortable. The other thing that's sort of interesting to look at, here's some statistics that Boeing put together in terms of their projections of comparing last year and 20 years from now, how many of all of these different size aircraft are actually active in the fleet, and what do they expect to happen? And in almost every category, you can see growth. So these big A380 type ginormous planes, there's going to be a lot more of those. There's going to be a lot of the Dreamliners, 777s, all of that. There's going to be a lot more of the 737s and the smaller things that we probably spend most of our time on. The only thing that's going to go down is these little regional jets. That was a bit of a fad. It won't go away entirely, but they won't find quite as much use as people had originally thought. So here's the picture that's supposed to give that last projection a little bit more credence. This is also from Boeing, but it's basically data that they collected from an international organization that keeps track of what's going on in aviation. This is a little bit different in the sense that this is revenue passenger kilometers. So this is the number of passengers times the number of kilometers that they flew. So you could make this graph get bigger either by having more passengers or by having them fly on longer flights. And both things have happened. You can imagine the growth of traffic between the US and Asia, for example, has caused a lot of flight lengths on average to increase. But what's important that's contained in this graph, you say, well, you know, I don't know, how much can we trust these kinds of projections? It seems that world events seem to have a pretty big impact on what's going on. Here's the list of sort of important things that happened over the course of this graph, yet any decent statistician would probably still be willing to hold their hand up at an angle sort of like this and say, you know, that's not bad and no good reason why we shouldn't expect that to continue in the future. Okay, so each of these slides is supposed to tell sort of a small piece of the story. So the first part of the story is that we're going to have more air traffic. It's going to get busier, and for those of you who fly a lot, you already know that it's already busy. And because it's already busy, you experience cancellations and delays and misconnections and all these kinds of things. This picture, yes?
Just a minor question regarding that graph that you showed.
Yes.
What happens to the cost of travel as the year goes on?
I think the economics they're a lot different because fares, I don't have a good picture of what has happened to fares on sort of, you know, the same sort of market segments over the same period of time. If that's what you mean, like how much are you going to have to pay? So that's probably going to go up too, and probably at more than inflation. The fuel prices are playing a role in that. There are probably going to be different ways of assigning taxes and user fees that are going to change. So we're probably going to end up paying a bit more. But I try not to be too much of an economic prognosticator. So this picture comes from the master's thesis of one of our students. I put it up here for two reasons. I'm happy that the text is small because you're not supposed to zoom into the picture very much. You're supposed to get sort of a blurry vision of what it means. It's a design structure matrix. So one of the things you're supposed to do is say, oh yeah, that has something to do with the stuff that we teach around here in the systems engineering master's degree program. So that's one of the reasons I put it up there. The other reason I put it up there, what she was trying to do is she was trying to say, look, here are all the things that are sort of performance measures and metrics that we can look at airports, and here's those same things listed this way. And what the spirit of this diagram is supposed to be capturing is how these things interact with each other and how they're related to each other and the extent to which the sort of the strength of those relationships. And the point is that there's big groups of things that are all not the same thing, but they are all intertwined in very complicated ways. So that's really the gist of the picture. The previous picture was that air traffic is growing. This picture is whether it's growing or not, it's complicated. There are tons of competing and conflicting things that happen within the airspace system at individual airports that cause the whole system to be an enormously complicated thing to study. Here's a picture from one of our PhD students from a few years ago that's trying to illustrate just one small slice of what I just said. We look at a lot of performance measures. This is something that you would be very familiar with if you fly. The plane said it was going to take off at such and such a time, and it didn't. And what are the reasons that that could happen? Well, here's a lot of them. You know, things like weather, things like the things that you're sort of used to. The pilot will tell you that a piece of the plane fell off, and you have to wait for them to bring another one. You normally don't want to hear that. Or the crew was drunk, so they had to get another one of those. Or all of these different kinds of things. And there's more than just this, but each one of these things is an added complication that we have to worry about. And delay, I think, is something that we talk about a lot because it's something that the individual passenger experiences and really can strongly relate to. Their goal is to be at a certain place at a certain time, and they've sort of reverse engineered their schedule so that those things happen. And when you come along and you tell them, no, you're going to be an hour later than you thought you were going to be, depending on how they had stacked things up after that, that could have a pretty big impact on them. Delays themselves, just looking at delay, is complicated and messy. Here's a plot from that same thesis that shows 365 different days out of the year at one particular airport. I don't remember which one it was, but delay is a function of the time of day. You'll see all kinds of stuff in here. You'll see, of course, a lot of the days are different. They don't tend to cluster together terribly well. but you also see these up and down spikes. So whichever airport this was, it's an airport that's serving as a hub, because you have a lot of planes that are sort of coming in these big banks, so that people can get off one and get on the next one, and they all have to be sort of in the same place at the same time, so people can do that conveniently, and then they all fly away, and then the airport's not very busy for a little while, and then a whole other big clump of them comes in, and everybody runs around for a while, and then it takes off, and so forth. And you can see this periodicity that's evident in the slide, even though we've plotted.
It seems to be synchronized from day to day.
Yeah.
It's not just
From day to day, and
just
oddly enough,
schedule.
it peaks almost on the
Right,
even
the
hours.
hours, yeah, sure.
Right.
Number of peaks and number of hours.
And the reason for that is almost a psychological explanation. If you are trying to buy a ticket, all of these delays are tied to the time that the plane was supposed to take off. If you buy a ticket and the ticket says that you're going to leave at 11 o'clock, you like that because 11 o'clock is a number that you can remember. You know you're supposed to be to the airport and on your plane by 11 o'clock. If somebody sells you a ticket that says you're taking off at 11:47, for whatever reason, people don't like those kinds of tickets as much because that's in their head, that's a different kind of animal to try to schedule themselves to. So their little Outlook thing doesn't like 11:47 very well, and all of that.
But your iPhone is
Yeah, I mean, maybe in our heads we'll get used to a better sense of time as a continuum. But. Okay, so with that backdrop, aviation's complicated, it's busy, and it's only going to get worse. Enough noise was made, enough complaining happened, enough Congress people got involved and so forth that somebody said, all right, we've got to do something about this. So we're going to write some laws, we're going to create some new things, we're going to put a bunch of people to work on this problem, and we're going to see what we can come up with. So this next generation air transportation system, NextGen is its most recent moniker, was created in 2003 as part of the Act reauthorizing the FAA at the time. You've probably read in the news recently that the FAA is not currently reauthorized, and they keep moving from continuing resolution to continuing resolution. Nevertheless, this is one of the last times that they were officially authorized. As part of this, they created this Joint Planning and Development Office, which essentially means representatives from all of these important agencies all have to get together and form committees and working groups and have meetings and panels and projects to figure out what are we going to do about this, what's thought of as unsustainable air travel demand growth. So you can see sort of the obvious things: the Department of Transportation, Homeland Security, Federal Aviation Administration, NASA, but there's also the President's Office of Science and Policy is there, DOD is there because they have a role to play. Department of Commerce is there. All of those people are involved. You can't do a big government program without having org charts and structure and offices and blah, blah, blah. So this is kind of a big overview of who's involved. There's a management council, there's this institute, there's, in addition to sort of doing the work, there's teaching that's going on. And then there's the architectural point of view that says, okay, well, what are we actually going to do? There's sort of information technology components. There's interagency operating. There's all of these myriad things. So this is thousands of people that are sort of involved in this. What's the sense of what they're going to be able to pull off? Their guess, if we just look at annual delay minutes accrued across all of the passengers in the U.S., this is, that very top solid line is what would have happened if we just left everything the way it was and let air travel grow the way that we expect it to grow. So this isn't building a whole lot of new runways or adding any kind of traditional capacity, just sort of letting things get worse. So if you think things are bad now, whatever sort of pain you want to assign to what you feel now, you can see that more than doubling over the course of this projection. If we put a whole bunch of money into building some runways, we might be able to reduce that by a little bit. And with the technological improvements that they're talking about, they're seeing maybe we can get down to about here. Now, don't be too dismayed that the curve still seems to be rising, because that's against the backdrop of the fact that more people are going to be flying. So if you divide that by the number of people that are actually flying, your personal experience, which would be the ratio of those two things, might actually be a little bit better. Because this is aggregated across everybody, but the size of the everybody is actually going to grow. Okay, so what are the sorts of things that we do to participate in this program? We do a lot of work on what we call resource rationing. In the United States, air carriers, for the most part, except at a few airports, can decide by themselves, purely autonomously, what they want to do. They say, I want to schedule a flight and I want to go from here to here. As long as they're certified to fly that particular airplane and to land at that particular airport, and as long as they have a contract with the people at that airport to come out and refill the plane with fuel and to deal with the baggage and to put sandwiches on board and all of that, they're perfectly free to schedule a flight into that airport at whatever time they want. Nobody can tell them otherwise. And by accident, most of the time, they set all their schedules, and they're thinking about, well, what are my competitors doing and all of this, but they also know what do my clientele want to do. They schedule all of these flights, and purely by accident, most of the time in most places, the planes can take off and land with very little interference. But also by accident, what tends to happen every now and then is more people schedule themselves into an airport than the airport can handle at any given time, and then somebody has to say, okay, we're going to have to do something about that, because we can't have them all arriving and trying to land on top of each other. And this is one of the things that air traffic controllers are responsible for, is to figure out that this is happening and to start pushing these planes back, or pushing them to the side, or having them fly around in circles for a while until they sort themselves out into an orderly system. Of course, the other thing that happens is that Mother Nature comes along every now and then. In the summertime, we'll throw thunderstorms and hail and rain and snow in the winter and all of these kinds of things at you. So whatever you thought it was that you could do nominally, now you can do even less than that. So sometimes on a contingency basis, somebody has to come in and start slowing things down. So when you slow things down, this is what we mean by rationing. Somebody has to come in and decide, okay, we can't do this as rapidly as we thought we were going to be able to, so we're going to have to slow things down. So moving backwards, okay, you can land here. You thought you were going to land at this time, but now you're not going to be able to do that. We're going to have to move you back to here. And then you're going to have to go back to here, and so forth. You can't tell the aircraft that news while it's in the air or while it's sort of swimming around in circles by its destination. It's not terribly safe to have a whole bunch of planes flying around in circles next to each other. They don't like burning all of that fuel. The people on board the airplanes get really nervous if the plane spins around in circles for too long. So the much better thing to do, if you knew about this far enough ahead of time, was to catch the plane before it took off and say, look, you were planning on taking off here and landing here, but we're going to have to move your landing back by here, which means we're going to move your takeoff back to here, and then everybody either sits on the plane or they go run around the terminal for a while, but at least they're not in the air causing problems. The idea of the rationing is that somebody has to figure out, okay, who's going to tell each one of those planes what their disposition is. Some of them are going to be delayed a little bit, some of them are going to be delayed a lot. They all compete with each other. Nobody wants to be the one who gets a lot of delay. They all want to be the one who gets a little bit of delay. So it's this big sort of argument over what's going to happen to everybody. We help design the rationing mechanisms that decide who gets delayed and by how much, and to try to make that fair across different carriers and across different markets and so forth. I was on a plane one time, and the pilot came on the thing and said, the intercom, and said, we're not going to be able to take off right now. There's weather where we're planning on going, and the FAA has decided that we have to sit here for an hour. So, get comfortable, and I'll let you know when we know more. And the person next to me, I swear this happened, said something along the lines of, gee, I'd sure like to meet the guy who makes these kinds of decisions, or something like that. I said, yeah, boy, I would too. So, that's not the sort of thing you advertise when you're running around. We also do lots and lots of work on analyzing the performance, just figuring out how will you say what was a good day, what was a bad day, predicting how that's going to change. We do Large-scale modeling and optimization. So you can guess that this decision process with rationing and with other things of deciding who goes when, those are usually formulated as gigantic optimization models. Sometimes they're solved differently, but usually we at least start by thinking about what our objective is and what our constraints are and all of that. We help with policy analysis. Occasionally the FAA comes along with these brainstorms and wants to know, well, what do we think is going to happen if we do this or we do that? Market mechanisms. So one of their brainstorms is what if we start charging money so that maybe as many of these flights as thought they wanted to schedule into a particular airport don't do that anymore, because each one that wants to has to pay in order to get in there. So we work on that, as do a couple other people in the room. Benchmarking. Our biggest effort at benchmarking recently has been comparing the United States and Europe, because the two systems work quite differently. Both sides have things that they're proud of, and both sides have things that they complain about. And we had a joint effort going on across the pond to try to figure out, okay, well, what is it that you do, and how is it that the thing that you do produces good results here and bad results over there, and similarly, what is it about the way that we do things that causes us to do things in a certain way? And then economic impacts. We had another big study recently where we were looking at all of this time that everybody wastes, waiting and being delayed. What is the overall impact to the U.S. economy on that? And really, you can imagine what the goal there is. If you can figure out what that relationship is, then you can talk about, well, if we can improve the delay situation, we're essentially saving X number of dollars to the economy. Therefore, we can make a case for spending about X number of dollars, or maybe slightly less than that, to make these technological improvements in the first place.
Dave,
Yes?
I know that collaborative decision-making is and has been part of the research program for a long time.
Yeah.
How much of that is in practice now, like related to the resource rationing mechanisms, versus just whatever the FAA say?
A lot.
Decision maker?
A lot, but there's still stones to turn over. So we have current projects that are thinking about new twists to put on that, but I have a slide in just a second that kind of illustrates that a little bit. It's a good question. So if I skip past that, remind me. Here's a recent slide whose subject is basically some new rationing mechanisms. What happens right now, for the most part, is if it's time to start thinking about who gets to go next, that's mostly decided on the basis of the order in which you scheduled yourself into the airport. So they look at what would have happened had there been no weather and had there been no capacity problem. What was the sequence of flights that were going to show up? Let's just take that same sequence and move it back. The problem with that is, if you imagine a flight, let's say, from San Francisco to Denver, and for a while there were thunderstorms in Denver. This happens a lot in the summertime, and so a lot of the planes were delayed. The practice right now is that you don't act. If you've been held on the ground at San Francisco waiting for your opportunity to get to Denver, you don't get to take off until the weather actually clears in Denver. But it takes a couple hours to get from San Francisco to Denver. So by the time the weather clears, in all honesty, if you had had a very good crystal ball and knew when the weather was going to clear, you could have taken off 2 hours ago and got there just as the weather was clearing, and everything would have been great. But that's sort of deemed to be an unsafe or too risky way to go about business, so we don't do it that way. A different way of thinking about that, rather than rationing these flights by the time sequence, would be rationing them by how far away they are from the airport. And give the ones that are farthest away first crack so that they don't end up in that situation. The ones that are closer, if all of a sudden the weather clears, getting them in to fill those newly available slots is much easier, because they're only a half an hour away, whereas you're not worried about these flights that are hours and hours away. Of course, like anything, you can't do it lock, stock, and barrel, because there are entire carriers whose business model is to fly short flights. So if you say, oh, hey, our new scheme is to screw the short flights and advantage the long flights, well, United and Continental are all going to get excited, and Frontier and Alaska and other carriers are going to be routinely left in the dirt, and they don't like that. So we have to do, you can have sort of a primary basis for your rationing, but you also have to think about the effects that it has on all of these other things and figure out a way to put those into your mechanisms. This is another slide that I like because it is something that could come out of our MSSE curriculum. It's just, you can imagine it's sort of a Pareto curve of an expected delay measurement and basically a metric that says how far away you were from where you would have been if we had used the time-based scheduling. Those two things sort of end up trading off against each other in patterns like this. Here's 3 different versions of the rationing mechanism that we were thinking of. But basically, any point on this green curve is, in some sense, sort of equal to any other point on the curve. You'd have to decide how you wanted to weigh this metric against this metric before you could make some sort of decision as to where you wanted to fall. This is sort of another way of looking at the same thing. Here's a bunch of different airports. And if we look at this parameter that sort of talks about how do we make sure that using this distance-based scheme, these short-haul flights don't get too bad of a disposition, how do our new algorithms compare to what would have been done under the time-based rationing? I said that we do a lot of performance analysis stuff. Here's us looking at Atlanta Hartsfield as a queuing problem. And basically the thing to take away here is that we built a bunch of different models. And one of them, the red model, essentially contains almost no variability. And what we're using that for is a proxy for what's going to happen 20, 30 years from now with all of this new technology when we are so certain about what's going to happen with each flight that we can really sort of tune in very tightly on all of our operating parameters and do a much better job. So you'll see that in terms of delays, operating in that fashion does a lot better. The blue one, which we call stochastic, is essentially a representation of what's going on today. So we use this picture to illustrate sort of the bookends between how things are working today and how much better they could be, even over the course of just one day, with respect to a delay metric, if we do a full deployment of all of these new technologies. We do this sort of modeling in lots of different ways. Here's a picture of diffusion models that one of our students was working on. And this shows sort of similar things. And the point of this picture was really just to show that we did a good job building the model. But we've done this for lots of different airports, lots of different scenarios, lots of different time periods and so forth. Here's another problem that we worked on. I said that we're going to see more and more planes, and some of the planes that we're going to see more and more are these gigantic things like A380s, assuming that the engines don't catch on fire and fall off the side of the plane, which has already happened once. Well, it didn't fall off, but it caught on fire. They're expecting to see lots more of these things, particularly at places like Los Angeles, because the Asia market, China and places like that, are expected to start really sending a lot of people in this way. A380s are already coming into Los Angeles from Sydney and from Singapore, and maybe there will be even more of them.
San Francisco is the same.
San Francisco has tested them.
Has tested.
They don't yet, to my knowledge, they don't yet have regular operations into San Francisco, but
They
they've
did Lufthansa.
Lufthansa,
Yeah.
okay, so that's probably recent.
Yeah.
One of the tricks with those things is that you actually have to fly the aircraft into the airport when nobody else is there and start asking yourself, what's going to happen when this giant plane gets here?
Exactly.
You might remember in the news not too long ago, an A380 was going down a runway at JFK or Newark? JFK, and actually clipped another plane as it went by, spun that other plane around in a circle, and people on that plane were not terribly excited about that. These A380s are so big. At Los Angeles, this is the south runway complex. There's 2 parallel runways on the south of the airport. There's 2 more on the north. If there's an A380 using one of these runways, nobody can be on the other runway. Other combinations of planes, that's not true for, but the A380 is so big, and you always have to allow for the fact that it isn't necessarily going to be going right down the middle of the runway. Even when it's landing, it's going to be all over the place. The other constraint you have is that even once you're off the runway, you start driving around the regular parts of the airway, you can start smashing into stuff. So there's only certain terminals you can use, there's only certain taxiways you can use. These things are behemoths, and sometimes you don't figure these things out until you actually sort of get the plane. You have to have special procedures. You have to have special ways of knowing who's coming and who's going, and where do you hold all of these other aircraft to make sure they don't end up in the wrong place when the A380 is going by. So we were working on helping them design the procedures for certain airports and building this sort of thinking about what's going to be different when these things happen into a big simulation package that is used quite a bit in the aviation industry to model what's taking place in the U.S. airspace system over the course of the day. And this was the project actually that we worked on with intelligent automation. There were lots of other aspects of the project, but what we were doing was looking at particularly what happened to the big planes when they were on the ground, taxiing around, moving back and forth.
This project ended?
That one's done.
Yeah.
I said a little bit earlier about market mechanisms. We spent a lot of time, and Raghu has spent a lot of time on the same kind of idea, thinking about how are you going to start making people pay money for this constrained resource. Lots of economists would argue that if you have something that a lot of people want, and in fact more people want it than there are elements of that thing to give up, then the way to figure out who should get it is to make them start paying for it. And if they really want it, they'll pay for it. And if they're not willing to pay for it, then they must not have wanted it that much. The problem with things like this is if you go to a current airport and you say, okay, well, who has the right to land there now? And you say, okay, we're going to take that all away from you and we're going to start selling it to whoever wants it. A lot of carriers complain because they've put a lot of money into building terminal facilities and other things at particular airports that they don't want sort of swept under the rug tomorrow, and then they have to compete with everybody else when they thought that all of this time they had been establishing a presence. So one of our ideas was to take this stuff away from them in small pieces so that it wouldn't be quite as drastic. One of the other problems with this is that you start saying, okay, well, we're going to auction these things, or we're going to offer them up for sale in some other way in the market. What will the price be, or what should the price be? You don't know. The advantage to only selling, let's say, 10% of your available capacity every year is that you can do something called price discovery along the way. You can figure out how much people are willing to pay in the first year. You've only sold about 10% of them. That's a crude estimate, but you could start from there from the next year, and maybe the next year you'll fine-tune it a little bit. So Andy Turcho, who's right here, he had done this work for his master's thesis on developing kind of an iterative auction procedure that over the course of 10 years allows the values of the slots at different times of day to come into stronger relief. You can see that there are obviously times of the day when it's more valuable to be coming and going from an airport than other times. And basically to let that have an impact on how many of these things are offered for sale at all of these different times. It would be important, for example, if you knew you were going to have a lot of flights here and a lot of flights here, but not that many in here, to not allow very many people to fly in that middle part, so that if, for whatever reason, you did have some congestion build up here, you would have a chance during this time to let all of that stuff flush it out before you start again in the afternoon and get busy again. And that's sort of the rationale behind why this little bit shows up here in the middle. Okay, so these government people that are trying to figure out how we're going to do this, I say this with a little bit of cynicism. I sort of wish that they had spent as much money coming up with technologies and actual ideas for implementation as they did coming up with nice graphical designs of pictures with arrows and boxes and stuff. For years and years, you could find tons of pictures with arrows and boxes, and you couldn't find anything that talked about, well, what are we actually going to do? That's changing now, which is good, but still, you can get buried in these kinds of pictures, unfortunately. This is a little bit better description of where we think things are going. Right now, you could more or less describe our current navigation and surveillance system as ground-based. It's still the case that when the pilot is flying, he has to pay attention to these ground-based radar stations, or ground-based stations that he interacts with various radio equipment in the cockpit. And eventually the idea is to go to satellite-based navigation. So that seems like no big deal. Most of your cars already do it, but the aviation environment is very, very different. It has to be much more robust. Almost everything that goes into the cockpit has to go in twice in case the first one doesn't work anymore. There's all of these very stringent technical requirements that have to be met. There's still a lot of talk over the radio. It would be nice if people didn't have to talk that much. You can imagine many different information systems that are at play at once. It would be nice if somebody stitched them all together into something that was more cohesive. The aviation system relies very heavily on forecasts of the weather. You can get a weather forecast from about 25 different people right now, if you want it. They all talk about it in slightly different ways. They have slightly different models for doing it. They say different things. They have different projections. Which one is the one that we should be basing our operations on? It's still very much the case that if you can't see very far, then you don't get to do very much. Although with technology, that doesn't need to be the case, so we could do better there. And it's still the case very much that air traffic controllers are dealing with making sure this particular plane does not run into this particular plane. If there were more technology involved, some of that stuff could be sorted out automatically, and they would have more to do thinking about sort of big groups of planes and flows rather than individual aircraft. The mechanisms by which they're going to get there is this list here, and I've highlighted in yellow the things that we're working on. Something called performance-based operations and services. If you as a carrier buy new equipment for your plane, or you buy new planes that have the new equipment in it already, and therefore you are able to do more precise, more demanding things, you should be given more opportunities to do things as a result of that, and it's almost a feedback loop. They're trying to design this as an incentive. They're trying to say, if you buy it, we're going to treat you better, and because you're going to be treated better, it will be worth more to you, therefore you should go buy it. Rather than the FAA saying, hey, we're going to give you all a bunch of money to equip your planes, because that's an enormous amount of money, and it doesn't need to be done that way. We know more about weather than we used to. We know more about the statistical properties of weather, or the sort of stochastic aspects of weather. Could you, rather than being as conservative as we were saying earlier, where we don't know anything about the weather, but when we look outside and the weather has cleared, then we'll feel free to send all the planes. Rather than being that conservative, could you take a more stochastic approach and think about, well, what might happen and how likely is it, and make some decisions based on something like that instead. Trajectory-based operations. Basically what this means is we're going to be a little bit less memoryless. Right now a plane goes up in the air, it sort of takes off. Occasionally a controller is aware of what's going on as it goes from place to place, but there's different kinds of controllers. The plane gets passed off various times along the way. When it's time, for example, for the plane to come in and land at its destination airport, when it gets to the terminal area, that's the first time. It shows up, it crosses the boundary, it calls the new controller and it says, hey, I'm here, what are you going to do about me? I want to land, fit me in somehow. That's the first time that person has ever, for the most part, has ever even heard of this flight. Yeah, it's a big surprise. And they're like, okay, well, I'll fit you in. You go here, get to this altitude, fly this heading, and so forth. They're trying to get to the point where they're thinking about the entirety of the flight. Where does it start? Where does it end? Draw a three-dimensional trajectory for that, and then throw in time as a fourth dimension. And now you have these sort of strings in four-dimensional space, and as long as you can intertwine these strings so that they keep enough separation between them, you could get everybody going where they need to go just by sort of pulling and bending the strings, rather than being quite so surprised. And then this is sort of obvious, high-density arrival and departure operations. Our constraint is that planes can only land so quickly at runways, and partly it's because they can't get too close to each other this way, they can't get too close to each other this way, they can't get too close to each other this way or this way. There are ways that technology can help improve those things, and essentially we'd be able to land more planes and to do so quicker. Here's your CDM slide. These rationing mechanisms. Here's how it used to work. There's weather, it affects the capacity, the FAA decides, okay, who's going to win, who's going to lose. A better way, which we've been working on for 10 years, is there's weather, the FAA says, okay, here, nominally here's what I'd like to do. The carriers say, well, okay, that's okay, but we're not completely thrilled with that idea. Because you moved one of our, you didn't have any idea of all these flights that were in some sequence, which one was more important than the other one. We might have one that's getting to a specific airport at a specific time because everybody on that plane needs to transfer to another plane and get to their next destination. We might have some other plane that just has to get there and almost everybody on it is going to stop there. So if that second one is an hour or two late, at least everybody's still getting to their destination. If the earlier one is an hour or two late and everybody on it misses their following connection and you don't have another connection until the next day because it might be JFK and flights to Europe, then you've really made a lot of people mad. You're going to have to pay for a lot of hotel rooms and meals and stuff like that. That's going to have plus you're going to start filling up tomorrow's flights, which are probably already mostly full anyway. So the whole thing can explode very quickly. So carriers want to have the opportunity to say, okay, wait a minute, I like sort of the idea here, but take my guy here and swap him with that guy over there, because in my mind those are more important. And in fact, this one here, you moved it so far back, I don't have anything to swap it with, but I don't have that many people on it, or I could always put those people on different planes. Why don't you just cancel that one entirely? Get rid of that one. One of the problems, this is what they would like to do. The substitution part is easy. The cancellation part, they would be willing to do themselves, but they would keep that thought to themselves. Because they knew that if they told the FAA, hey, I'm going to cancel that flight, the FAA would say, oh great, that's a slot that someone else can fit into. The problem is that someone else, in all likelihood, is that carrier's competitor. So they would cancel the flight, but if they couldn't use that slot themselves, they wouldn't say anything about it. So the new idea that was CDM was essentially, look, you can participate in this whole process if you tell us what's going to happen. And if you cancel flights in order to create slots, we're going to figure out a way to move your resources up into those slots so that you are actually the one that gains. If, when that's all done, a few other people move up as well, that's good, but at least you weren't just handing a golden ticket to your competitor. Here's the new idea. Because now we're going to have aircraft that have all of this new technology on it and can do all of these fancy things, maybe we take some of that capacity and we allocate it to people who don't have any of that technology, and we take some of that capacity and we allocate it to people who do have the technology. Then we let carriers make the same kinds of decisions they were making here. We let them make the same kinds of decisions they were making here. If some holes open up here, a better equipped airplane could still use one of these sort of old-fashioned slots. So there's still a chance for some movement to happen there within the same carrier. Then when you're all done, the FAA takes one final look, make sure there aren't any holes. If there are, it sort of shoves everybody a little bit farther forward, and you move on. So what are these new technologies that we're talking about? The big one is ADS-B, Automatic Dependent Surveillance Broadcast. I'm an airplane, I have a GPS, I know where I am, nobody else knows where I am, because that's all GPS does for me is it tells me where I am. I start yelling as loud as I can on one of these frequencies, here's who I am and here's where I am. I say more things than that, but those are some of the important things that I say. If the people on the ground can hear everybody saying that, that becomes a form of radar. It's not physical radar. You're not bouncing something off of the plane and measuring how long it took for it to come back and remembering where you were pointing when you did that and then plotting a picture of that. You're just listening to a bunch of people telling you where they are, and you're plotting that on a screen, assuming that you can trust them and assuming that they're all saying that. You'll still have the radar going at the same time as a secondary system. But the other thing that you can do, that's what we call out. So that's everybody sort of broadcasting. Here's who I am and here's where I am. The other part of it is called ADS-B in. An aircraft could be listening to all of its neighbors who are saying these same things. Now it has situational awareness. It knows where all the other aircraft are. That's something that they, for the most part now, don't have. The controllers on the ground know where everybody is. Up in the air, unless you can see them out the window, you don't know where they are. If you have certain parts of the airspace where only aircraft that have these capabilities are allowed to fly, then you could feel perfectly safe making certain kinds of maneuvers without interacting with the air traffic controller because you know where everybody else is. Lots of new information management stuff, data communication. So some of this stuff there's going to be more here than just here's who I am and here's where I'm going. There's other kinds of things, weather reports, other kinds of informational broadcasts that need to take place. I keep trying to reach for the keyboard and I have the stupid pen. So here's what we mean when we say performance-based navigation. It used to be the case that if you wanted to fly from point to point, you essentially had to navigate to a fixed waypoint. So there was a station on the ground, and you had to sort of know where that was, and you would fly towards that. And then once you got to that, you'd pick the next one, and you'd fly to that one. Once you got to that one, you'd pick the next one. The very first planes that were flying around were carrying mail, and they used to do this by moving from one bonfire to the next bonfire. And people got paid to go out at night and light giant fires so that a plane could fly from one bonfire to the next and know how they were going. And the more modern system isn't a whole lot different than that. They're radios rather than bonfires, but it works the same way. Once this RNAV system was installed, basically that says, rather than going from beacon to beacon, as long as I have the technology of sort of recognizing where various beacons are, I can carve a path that goes between beacons using telemetry and sort of measurements to these other beacons to get where I want to go. The only thing that lacks is sort of its own internal sort of testing mechanism to make sure that it's doing a good job. So the most recent version of this is this thing called RMP. It has onboard performance monitoring and alerting. And one of the things that they allow aircraft to do under this new RMP thing is they allow them to do things like change altitude at the same time that they're making turns. Which, if you think of military pilots, they do that sort of stuff all the time on the fly. But commercial aircraft, for the most part, don't do that. And there are places where if you look at some of the conflicting routes, that's what you want to do in order to make these streams of aircraft get along better. So here's sort of an idea. Here's the old system where you're flying from point to point. Here's the new system where you essentially invent these virtual waypoints. They're not actually stations on the ground. You just define a point up there in space someplace, and you fly between those. But you can do that because you know where you are relative to some of these other things. And with the new system, you can tighten that up even more. So here's a couple of pictures to show you what's going on. I'm sorry, let's see, I better get done here pretty quick. So let me blast through this, and then I'll fly to the end, and then if you have some questions, we'll take those. I'll have to skip a few slides. This is part of the New York area. This is Newark International Airport down here, and buried under here is Little Teterboro Airport. And planes that are taking off from Teterboro do so on runway 19 and 24 for departures. So they're coming out basically at 190 degrees or 240 degrees relative to magnetic north, and they're going off in all of these other directions. Because they're doing that, planes that are coming in and trying to arrive at Newark on 22, it's hard for them to manage those two flows, because the one group is taking off and the other group is trying to land, and they're crossing while they're trying to do that, and that's a nightmare. Particularly because you can see from the picture how accurately they're able to do this. This is a set of flight tracks superimposed on each other. They get real accurate when they get down on this instrument approach, but prior to that, they're all over the place. Partly because somebody probably told them to do that, and partly because they were staying away from somebody else that was also in the air at the same time. But the idea is to tighten up all of these approaches, make them much more organized, and you only have to do it at Newark. You can still let the planes coming out of Teterboro be sort of wild and crazy. If you can tighten up these other approaches, you can do a much better job. Another version of the same thing for, this is arrivals to Newark conflicting with aircraft coming in and out of LaGuardia. Just bad luck that the best way to align the runways at LaGuardia and the best way to align the runways at Newark with respect to the winds has them flying these planes into the same airspace. It's just their dumb luck, but it is what it is. It's also dumb luck that it also happens to be one of the busiest parts of the United States where everybody wants to come and go from. But if you could clean that up, it might look a lot more like this. So let me bounce ahead. I was going to tell you a little bit about these descents, a little bit more about stuff we've been working on, but let me just get to the last slide here. What are we going to continue working on as we move forward? We're still working on these resource allocation mechanisms, this collaborative decision making for allocating resources both at airports and in the air. We're working on terminal area procedures. We're still working on constructing metrics and measures for predictability. We're still working on a version of these mechanisms that we're working on are the ones that allow better equipped aircraft to have better service. Therefore, they would be willing to pay for certain things. These kinds of things are what we imagine working on at Maryland, at least, for the duration of the next 7 years of this contract. And you might have noticed as a final note that the set of departments and places on campus that we draw our talent from is pretty diverse, because this kind of research doesn't necessarily speak to just a single department. There are civil engineers, there are mathematicians, there are computer people, there are systems engineers, there are aeronautical engineers, there are business students, optimization people, there's a lot of queuing theory people, there's lots and lots of different kinds of people, economists, whatever, whose inputs and talents can be put to use on the kinds of projects that we work on. So we have a pretty diverse group of people. And with that, I guess I'll have to close. I'm sorry that we went a little long. In my defense, we also started late.
Excellent. You have some time for questions. Go ahead.
How does departure delay correlate to arrival delay?
It depends on what air carrier you are, and what your model is for turning your aircraft around. But usually quite highly. So somebody like Southwest, they are famous for shoving everybody off the plane as fast as they can, and shoving all the new people on as fast as they can, and getting out of there as fast as they can. So when the arriving aircraft is late, whatever flight that airframe was supposed to serve next is necessarily also going to be late.
And I'm going the other way. I'm saying your first couple slides talked a lot about departure delays.
Mm-hmm.
As a consumer,
Oh.
I don't really care about that. I want to know when I'm leaving 20 minutes late.
Right.
Does that mean I'm going to be 20 minutes late on my arrival?
No, nowadays it probably means you're going to still be on time. The pilot will generally lie to you and tell you that he's going to make up that time in the air. That's the only way to do that is to go faster. They don't go faster because you have to burn more fuel to go faster, and in the end it costs you more money to do that. What they've been doing recently is just building slack into the schedule. So when they originally told you what time they thought you were going to be there, they predicted that conservatively. So even if they're 20 minutes late, they can still make that target. You'll probably notice that more often now than 5, 6, 7 years ago, when you land someplace, they're telling you you got there early.
Yeah.
Yes.
You didn't get there early, they just pushed back.
And the flights are also long, especially East Coast flights, the
Yeah.
1 hour flights, they give it like 1.5 hours.
Right. Yeah, exactly. So the expected time to traverse.
Washington, Boston is now 1.5
Exactly.
hour, 1 hour.
It used to be scheduled as an hour flight, now it's an hour and a half.
That's
So the good news is you won't miss as many connections as you used to.
But sometimes they do go faster when
So-
they're really late.
They can,
Yeah.
but no one wants to have a system in place that incentivizes doing things that are either unsafe or that burn tons of fuel
That's true.
and produce emissions and all of that.
So is there a nominal, whatever, break point that, you know, if you leave by up to a half hour late, you kind of got to get there on time, but after that, you're going to be late.
No one at any of the carriers will tell you how much padding there is in the schedule, and they're not even willing to call it by names like that. What they're saying is they're just trying to do a better job of predicting when you will get there, essentially to ensure that when an itinerary is scheduled, that the computer doesn't put together an itinerary that has some reasonable chance of getting disrupted because of a late plane. So, you know, it's the computer that assembles these things together, and if you give it a tiny little window and there's a lot of volatility with one of those flights, then you could be in big trouble. So, I mean, in my own experience, I would guess 20, 30 minutes, but that's on the basis of a couple of dozen flights, so I don't know. There are people who are trying to do data mining or statistical analysis to go back and look at, well, 10 years ago, how long did it used to take flights to get from A to B, and now how long is it taking them to get from A to B, and how long did they used to say it was going to take,
That's
and
right.
now how long are they saying it was going to take, and then when you have a bunch of numbers like that, you can sort of ferret out what that difference is. Andy, does 20, 30 minutes, that sounds...
Yeah, I think so. It depends a lot on how long the flight is scheduled to be. So there's be more padding built in if you're going from coast to coast versus you're going from Washington to Boston.
Right.
And it depends a lot what airport you're starting and leaving from, because they build in a lot more time if you're leaving from, say, JFK, where there's these epic waits on the tarmac. to
What
get to
time of the
runway.
day, you know?
And
Yeah, what time of the
Day to
day,
day,
yeah, so
like
the
this.
20-30 minutes is a good
Yeah.
rule of thumb.
Yeah.
But I have found myself, in general, this is just anecdotal, much less panicked over connections the last few years than I used to be, which is good because I'm getting older and I can't run as fast.
Question, Nathan?
The next gen technology, what's sort of the big thing that's holding that back from being implemented? Is there like a resistance because of cost, or the technology is just not up to speed for the FAA yet, or?
The technology is good. One of the issues with aviation in terms of getting technology into planes is there's two ways to do it. You can put it on new planes. Then it's easy because it was probably designed into the avionics and the whole system, you know, all the electronics, all of the different tests and onboard diagnostics and everything else that was built in to begin with. And the cost of designing the aircraft was so huge that throwing in one additional box is not that big a deal. The problem is that airplanes last 25 years. You know, they generally retire right around the 25-year time span. So we've got a bunch of aircraft that are flying around out there right now that are 15, 20 years old. It's going to take you 25 years to flush out the entire fleet. Nobody wants to wait 25 years to solve the problem. So one of the things you have to do is you have to imagine possibly going to existing aircraft and at some point in their maintenance cycle holding them out even longer and then retrofitting them with this new piece of technology. The problem is that none of the other systems that are on board that aircraft were designed with this new piece of technology in mind. So if you're going to propose doing that, it's not, you can't say, okay, well, we're just going to plug it in and as long as it works, it works. It's not like buying a little box for your car, right? Everybody is completely panicked that this new thing that you put in there is going to cause E&M interference with the other technology that's on board. It's going to cause power or interruptions in either the power services on board or some of the data services on board that are driving the other pieces of equipment that are on the aircraft. It'll get too hot and it'll start a fire in the cockpit. There's, you know, a million different ways that this new device could cause problems if it wasn't fully thought out and integrated. So somebody actually has to go through this really, really long and arduous certification process that says, well, here's how this new thing works. We're going to test it under every imaginable circumstance. We're going to stress test it in every possible way and validate that it can be incorporated smoothly. It isn't going to cause a detrimental effect in the cockpit or to any of the other systems that are active, to the procedural part of what the pilot has to do. People have to be retrained. So it's...
Do you think it's going to be mandated eventually? I mean...
No,
Some things are mandated.
Well, yeah, I figured, yeah.
They're going a few routes with that, so some things are trying to sort of encourage.
If you're going to be flying from here to here, you need to have...
Yeah, so for instance, Dave talked about
certain routes.
ADSB. ADSB out is mandated for all aircraft in certain kinds of airspace by 2020.
Right.
So you just have to buy it.
So the word mandate means if you want to go here,
Yeah, right.
then you have
So they don't have to do it.
You don't have to do it, but if you don't have it, you can't go here.
Gotcha.
Or you can't get to here by a certain, they have RMP routes that are now available. If the plane is equipped and the people on board are certified to use the equipment, if everything lines up nicely, then you can declare yourself in your flight plan to be eligible for a certain kind of route, and presumably that route allows you better access to the airport than other people would have. So they're trying to do it by way of incentive rather than by way of mandate.
So on that note, from the time that they come up with the new methodologies, like what comes out of your research, how long does it take on average for that methodology to be implemented?
It can take quite a while because we're not, as you can imagine, we're not systems integrators.
Right.
So, and in fact, you know, if you went to the control center now and you said, okay, show me the thing that Maryland did, it's not necessarily going to jump off the screen at you because it's been stirred in a big pot with everybody else's ideas, and then at some point some integrator had to sit down and read all of the papers and the thesis and say, okay, well, what's the gist of this? What were they trying to do?
Yeah.
Now I have to make a code that does roughly what they had in mind, you know. So I would say, I don't know, 5 or 6 years at least, something like that, just to have everything filter through all of the...
And then does it get implemented by other countries afterwards, or they use the different...
It does. Europe is very, very similar to the US. With respect to these technological innovations, there's so much traffic across the pond that except for a couple of frequency issues and a couple of details, Europe and the US are pretty much in lockstep with how that's going to be done. And that, to be honest, that's due in large part to the fact that we all buy planes from the same places, right?
That's true.
Boeing and Airbus and then a few other manufacturers for smaller planes. But if it's technological, it's going in the aircraft. So the aircraft manufacturers have as big of a role as other things
So,
do.
that makes sense.
The difference might be places like India and China that have fledgling aviation industries that are expected to grow by leaps and bounds. They might do the same thing with aviation that they did with cell phones, which is to beat the pants off the US and Europe by the time they finally decide to do it, because they can leapfrog all of the other old-fashioned things that we did on our way to the new technology and just aim straight at the new technology.
The new technology.
And there's a lot of people hoping that that's exactly what will happen, because then those
Because then
places
it
become,
forces, yeah.
it causes a pull effect from the front. It also gives you a better impression of, well, what are the benefits? We estimate them and predict them and model them, but you don't really know until you see the stuff.
In a way, it's not bad to let them try it.
Yeah, sure.
Anyhow, let's thank our speakers. More cookies and stuff like this, so help yourself.